Hi, my name is Andy Wei and I'm from Sugar Land, Texas.
Hi, my name is Anamika Chakrabarty and I'm from Northfield, New Jersey.
And today, we will be presenting our research on the integration and comparison of flood risk assessment maps and flood inundation maps to improve accuracy and prediction through machine learning and GIS. The goal of our research was to see if risk maps can be validated by comparing predicted risk locations with post-event inundation map classifications. We also wanted to use ISAT2 data to validate DM products and identify erroneous potential areas caused by spatial resolution when used to create flood risk assessment maps. We also wanted to use a classification and regression tree predictive algorithm that is used in machine learning to create flood inundation maps from Sentinel-1 data. So what's the difference between flood risk assessment maps and flood inundation maps? Flood risk assessment maps evaluate and depict the likelihood of flooding in specific areas based on factors such as historical flood data, topography, rainfall patterns, and potential sources of flooding. Flood inundation maps show the extent and depth of flooding during an actual flood event, typically based on predictive modeling and real-time data.
Risk assessment maps are an indispensable tool that are crucial for first responders and disaster planners to reduce flood risk potentials and determine real-time event management procedures. The relevance of these maps continue growing as climate change exacerbates the intensity of extreme flooding events on both a temporal and spatial scale.
We use a multi-instrumental approach for our research, utilizing data from ASTER, ISAT2, and Sentinel-1. First, we used ASTER on the Terra satellite to gather DEM data on the areas we were studying. We used ATLAS on ISAT to compare the ASTER data's accuracy, using the ATO3 and ATO8 data tools. Finally, we used Sentinel-1 data to visualize flooding in our areas of study through inundation maps.
We used Earth Data Search to get both ASTER and ISAT2 data and the Data Access tool, and Open Altimetry to get ISAT2, ATLO3, and ATLO8 data products.
We used three softwares to process and visualize our data: ArcGIS, FOREAL, and Google Earth Engine. ArcGIS was used to create flood risk assessment maps through DM data, FOREAL was used to process the ATO3 and ATLO8 data, and Google Earth Engine was used to create flood inundation maps through machine learning. We investigated two regions. First, we looked at Charleston in South Carolina, which experienced heavy flooding after Hurricane Matthew, which made landfall on October 8, 2016. Secondly, we looked at counties in southeast Brazil that are near the city of Sao Paulo, which experienced heavy flooding after torrential rain on February 19, 2023.
For our Google Earth Engine maps, we use Sentinel-1 synthetic aperture radar data, SAR, which is particularly useful in flood inundation mapping techniques due to the frequent revisit time, ability to collect images regardless of weather condition or cloud cover, day-night capability, and penetration through vegetation. As for our approach, we applied supervised classification using a classification and regression machine learning technique. We use Sentinel-1 SAR C-band data. There are 4 modes that Sentinel-1's radar can operate in. We are using the Infometric Wide Swath Routine Collection for Land, which is the main acquisition mode over land and is the one that is best used for flood mapping. The database used from Google Earth Engine is Sentinel-1 SAR GRD C-band synthetic aperture radar ground range detected log scaling. These images are all already analysis ready.
Creating a flood risk assessment map involves a systematic approach. First, DM data from ASTER was acquired through Earth Data Search. Next, the collected raster datasets were uploaded to ArcGIS, and within ArcGIS, the elevation data was visualized to map out the topographical landscape. The elevation was then categorized into 4 risk levels to assess flood susceptibility accurately. However, it's important to consider limitations. Elevation is not the only factor that plays into flood susceptibility, and an area of improvement would include having a weight overlay of more data features, including precipitation and vegetation. This is a flood risk assessment map of Charleston. We determined that Charleston has a relatively high moderate risk of flooding, and this is due to its low elevation. Along water bodies, Charleston has a very high risk of flooding, and as we moved inland, it becomes a moderate risk. In order to validate our flood risk assessment, we had to compare our DM data to ISAT2 data, since ISAT2 produces much more accurate data than ASTER due to its instrument. The ATO3 and ATLO8 data was processed in FOREAL, and the GroundTrack1 KMO file was plotted on the Charleston map. We then had to filter the GroundTrack data to remove the unclassified data points, and the map on the right shows the data points that we used to compare the DEM and ISAT2 data. This is a scatter plot that compares the DEM and ISAT2 data. ISAT2 plots the ground, vegetation, and the top of the canopy, which is why there are 3 datasets for it. ASTER only includes DEM, so it has 1 dataset. The graph was plotted with northing by elevation, and the data for elevation are relatively similar, with only a few anomalies, meaning that our flood risk assessment map was rather accurate.
Why radar data from Sentinel-1? Well, Sentinel-1 synthetic aperture radar, SAR, is particularly useful in flood inundation mapping techniques due to the frequent revisit time, ability to collect images regardless of weather condition or cloud cover, day-night capability, and penetration through vegetation. There are 4 modes that Sentinel-1's radar can operate in. We're using the Infometric Wide Swath Routine Collection for Land for the purposes of flood mapping. The database used from Google Earth Engine is Sentinel-1 SAR-GRD C-band data. As for our approach, we employed supervised classification using a classification and regression machine learning technique. This slide explains our basic, method, and process for the code. This video from the NASA RSET 2019 video series is what we based our models on and explains the coding process thoroughly. To dive into our process, firstly, we gathered the training data from the GEE database over our region of interest and on the days we are interested in. The before and after flood images may not be available immediately after or before a flood, so you have to adjust the time to when Sentinel-1 recorded data over that region. You must also apply a speckle filter due to the backscatter nature of the SAR data. Then you need to train your classifier to teach it what the visual change statistics look like, and you do that by creating layers of your different land covers you're interested in. So you overlay the training areas over the region and select areas that are representative of the backscatter that land cover layer shows. Here I am selecting flooded vegetation. Here is the before flood SAR image of Charleston, and then here is the after flood image. Here's them both so it's easier to visualize, and as you can see, certain areas appear brighter and there are visual changes due to the backscatter nature of those flooded areas and new darker areas from open water flooding. Here's the classification image that was created on Google Earth Engine through the CART machine learning algorithm and a key that shows the different land covers represented. CART is an incredibly powerful innovation in flood maps and semi-automatic classification of land cover changes that bring a lot of new insight to hydrological studies. However, this model does have some limitations which can be observed in this map of Brazil. This is the before image, and this is the after image. It is important to note that the time the image after the flood was taken is longer than the ones derived before Sentinel-1B was retired due to the revisit time changing. The classification map struggles with identifying the flooded vegetation change as there is a lot more elevation variety and a lot of vegetation, and there are many little changes in comparison to Charleston. It is also falsely recognizing the urban areas in the top left and on the right side as flooded vegetation because both flooded vegetation and urban areas exhibit the double bounce backscatter effect and appear bright, so it is easy for the classification to confuse them, especially when there is so much variation in elevation and there is heavy vegetation. Here is a close-up of those areas of flooded vegetation and of the urban areas, and as you can see, they both appear bright due to the double bounce radar backscatter nature. Overall, it is important to consider wavelength, polarization, and incidence angle when encountering limitations like these, as those parameters influence satellite response. Wavelength especially is an important parameter in heavily vegetative areas like the observed region in Brazil. SAR data is operated at the C-band wavelength, which has its own benefits, but there are longer wavelengths that can penetrate through vegetation canopy better. And here is a representation of how wavelength can influence detection of flooding. In the future, it'd be interesting to look at this map from a different wavelength. So, to overcome limitations in these classifications in certain regions, different wavelengths can be considered. Urban areas can be better distinguished from flooded vegetation through selection of more representative data. Also, as stated by Erica Podest of JPL at NASA Goddard Space Flight Center, the use of texture measurements, which provide information about the pixels, can also help to distinguish those areas from each other.
This is a flood risk assessment map of some towns near Sao Paulo on the coastal side. We determined that there are some areas with higher elevations, which are mountain ranges, as well as lower elevation areas. We saw that the coastal side was very susceptible to flooding and had a high risk, and as we moved inland and past the mountain range, there was moderate to low risk. Similar to our process with Charleston, we have to compare our DEM data to ISAT-2 data, and these are the tracks and data points that we use to compare the data sets. This is the comparison graph of the DEM and ISAT-2 data for the towns near Sao Paulo. The scatter plot is graphed by northing by elevation, and we removed the initial northing data points since it indicated water. From the graph, we determined that the DEM was an accurate representation of elevation since the data points are relatively similar and that our risk assessment map for Brazil was accurate.
This research observes the synergy between risk assessment maps, elevation profiles, and inundation maps, working in tandem to help enhance flood prediction and validation processes. By leveraging risk maps, the accuracy and precision of SAR database maps can be effectively validated and refined. Furthermore, flood maps generated through CART can allow for the identification of previously unnoticed patterns, thereby leading to improved flood predictions. Flood risk assessment maps and flood inundation maps are important on their own, but together they powerfully complement each other to improve hazard management responses.
Thank you for listening to our presentation. We would like to thank the SEAS program for the incredible opportunity to work in a professional research setting with our amazing mentor, Dr. Simurda, who helped us extensively on this project with her dedication to our team and projects. We would also like to thank Mrs. Margaret Baggio and Mrs. Selena Miller for their hard work and effort for making the program as amazing as it is, and also the chaperones and faculty that helped put the program together. We were able to dive deeper into our passions and learn new skills